In this video, we'll do some simple calculations regarding the orbits of Phobos and Deimos, moons of Mars. We are going to ignore the effects of other planets on the moons, and we are going to assume circular orbits. This is a very good assumption. The orbits of these two moons are extremely circular. So the questions we'd like to answer here: what are the orbit periods for Phobos and Deimos? How long does it take them to complete one orbit around the center of Mars? And if we're an observer on the Mars, could we make some statement about where these moons rise and set? So we're going to answer those questions. There'll be a second video that has more details about observing the moons if you're standing on Mars. So we're going to do this calculation for circular orbit, and our method of approach here will be that the gravitational attraction between Mars and the moon supplies the required centripetal force to achieve the circular orbit. So we can make a little picture here with the sort of shaded circle being Mars and the open circle being Phobos. This is not to scale. The size of Mars compared to the size of Phobos is not correct, but I just did it so I can fit it on the paper. But as we start the calculation for centripetal force is on the left side, on the top here, the mass of the object that's in orbit times v squared over r, which is the centripetal acceleration. This is the centripetal force. And now the gravitational force is supplied by the calculation of the universal constant of gravitation, capital G, mass of Mars, mass of Phobos, and divide by r squared. Well, we can observe that some things cancel here. The mass of Phobos appears on both the left and right side, so I'll cancel that. There's one factor of r in the denominator on the left. I'm going to cancel one factor of r on the denominator on the right. And then I'm going to take advantage that the speed, the velocity, the magnitude of the velocity, is found by the distance traveled, 2 pi r, is the circumference of the circle, divided by the orbit period time. And that's what we're seeking here. So I make that substitution for v and square it over on the left side. The v squared that was here gets replaced with 4 pi squared r squared over t squared. And now we have g, mass of Mars, and divide by r. Well, we can cross multiply here. 4 pi squared r cubed. Divide both sides by g and the mass of Mars. Multiply both sides by t squared. And we come up with a formula for the period squared. And now we'll solve this, putting in constants that are appropriate for the situation here. The orbit size for Phobos, 9375 kilometers, so 9375 times 10 to the third meters. That has to be cubed. 4 pi squared, the universal constant of gravitation, the capital G, and then the mass of Mars, 6.42 times 10 to the 23rd kilograms. That gets us t squared. You should pause the video and bring out your own calculator. I came up with the value of t squared as 7.59 times 10 to the 8th. Everything's in standard metric units here, so this is seconds squared. Take a square root of both sides. 2.75 times 10 to the 4th seconds would be the orbit period. And now converting to hours, if you divide by 3600 seconds is 1 hour, I came up with 7.65 hours for the time for Phobos to complete one trip around the center of Mars, so the orbit period for Phobos. And just on this next page, to remind us of a couple of the facts here, the orbit size for Phobos 9.375 times 10 to the 6 meters. The mass of Mars, I come up with the orbit period 7.65 hours. Repeating this process for Deimos, we have to change the orbit size. For Deimos, it's 2.3458 times 10 to the 7th meters. It's a larger orbit. Otherwise, things are the same. 4 pi squared, capital G, the mass of Mars. And again, you should pause the video and see if you come to the same conclusion I have for my calculation. I get 30.3 hours for the orbit time. So just in summary, Deimos, its orbit size 2.3458 times 10 to the 7th. Its orbit period 30.3 hours. And this is appropriate that it's larger than the orbit time for Phobos. A smaller orbit has a shorter orbit time. Now, just to remind ourselves of a few things here, if we think about our moon completes one orbit around the center of the Earth in 27.3 days. With respect to the stars, it's not with respect to the sun, not talking about time of new moon to new moon. That's a different calculation. Does our moon rise in the east or the west? What do you think? From your memory, hopefully you have observed the moon rises in the east and sets in the west. Our moon takes 27.3 days to complete its orbit. Our Earth spins once every 24 hours. In the situation where the orbit time for the object is larger than the rotation time for the planet, then that object is going to rise in the east. Well, let's think about what's happening here with Phobos. And I need to give you some information on Mars as well. But for Phobos, we get one orbit in 7.65 hours. The time for Mars to spin once on its axis is 24.7. Let's see if I can clear up this video just a little bit. Sorry about that. So Phobos, one orbit every 7.65 hours. Mars has one rotation in 24.7 hours. Here, the object of interest is completing one orbit in a shorter time than the rotation for the planet. And which object is going to move through 360 degrees first, complete one circle? Well, Phobos, having a shorter orbit time than the rotation time for Mars, Phobos is going to go through 360 degrees first, and that's going to have a consequence on where Phobos is observed to rise. Is it going to rise at the eastern horizon like our moon, or the western horizon? Well, I have a little sketch here, and perhaps you can pause and play around with the sketch on your own as well. If I can get the camera to focus on it just a little better. But I have Mars as the shaded object here, and I've put in a tangent line to the circle of Mars. This would be the horizon if you were an observer at this location on the planet. West is over here, east is over here. If you think about spinning, Mars takes 24.7 hours to spin once. Phobos only takes 7.65 hours to spin once. Phobos is moving faster around its circle than the observer is moving around the observer's circle here. Phobos is going to rise in the west. If you're an observer on Mars, this moon Phobos will rise in the west. What about Deimos? Deimos has one orbit in 30.3 hours. Mars is faster. Mars, one rotation, 24.7 hours. So which object moves through 360 degrees first? Mars is faster. Where is Deimos going to rise? Deimos is going to rise just as our moon rises, in the east. So we've In this video, calculated the orbit time using centripetal forces supplied by gravity, and then we've reasoned a little bit as to where we would observe these moons rise. Our moon traveling around its orbit slower than the Earth spins once on its axis, slower time for the moon. So our moon rises in the east. Our horizon is catching up with the moon. For Phobos, that's not true. Phobos is moving faster in its angular motion, and Phobos catches up with the Mars horizon for the observer. Phobos rises in the west. Deimos is more like our moon, although the time difference is not as large as our moon compared to the rotation of the Earth. But we would, if we're on the moon, if we're on Mars, we would observe Phobos rising in the west. We would observe Deimos rising in the east. And there's a companion video that you should investigate here, and gives more information about how long it takes to get back to the same observing conditions for Phobos and Deimos. So take a look at my playlist and you'll discover that video. Again, if you have other desires to look at physics and astronomy videos, I do have a website where you can look at these annotated lists of videos. It's totally free. There's no registration. I don't collect your email address or anything. But for physics videos, physics.gpclements.com. Astronomy videos, astronomy.gpclements.com. And ask your instructor if you have questions.